All right, so we can divide calculus up essentially into two parts, right? There's called differential calculus and integral calculus. Neither of those are going to mean anything to you right now. But differential calculus is the first thing we're going to talk about. It'll mean a lot to you soon, those words, but right now they don't. This will help you. This is why differential calculus, essentially, it does lots of things, but the fundamental problem that it was originally designed to solve is this one. So let's get everybody, I want Chromebooks all down here. I want everybody to see this. This is too good to miss. So if we're looking at, let's look at some random function. And this is one of those things, and this happens a lot in calculus, where I'm going to say this is just like a picture relationship. I want you to be able to draw this picture. If you can draw this picture, you get it. Really, that's it. I mean, picture is literally worth 1,000 words here. So the function, let's just say the function looks like this. It's some random function f that on this interval is doing that stuff. Okay, and we want to know, for example, if this is point A, and actually let's call it point, I'm going to call it point X. I'm going to make sure, yeah, I'm going to do that. I'll call it X. So let's call this point X, and let's call this difference in X values on the X-axis. Let's call this delta X, and so this would be X plus delta X. Okay. So if I want to calculate an average rate of change between the values of the function at X and X plus delta X, that's easy. You know how to do that, right? What would I do? I want an average rate of change of the function. So in other words, I would be looking from this point right here, right, up to this point right here. Let me make delta X a little bigger. I want to make it a little bigger so it's a little more dramatic. Let's go out here. So we're going from this point up to that point. How would I calculate the average rate of change? Ren, what do you? Okay, good. So we need the y values, don't we? So what are the coordinates of this point right here? X. Well, we don't really know a number value, but this is the rule here. I'm just going to call this f using function notation. So it'd be, this is X and f of X, right? Everybody agree? Okay, and then this would just be the point X plus delta X, sorry. F of X plus delta X, right? Okay, and this is going to be, so there's the y value for that one. There's the y value for that one. And if I want to calculate an average rate of change, how does that relate to these 2 points right here? Rate of change just sounds like a slope, right? Rate of change always, rate of change can be always represented as a slope. So the slope of what?
The slope of X plus delta X.
Okay, but if I wanted to just draw like a line on here, slope is associated with a line, right? What line would I draw that would have the slope that's equal to the average rate of change?
From f of X to X
Okay.
delta X.
Okay, good. So yeah, so I'm going to draw, here's the line I might draw then, right? My line, it's going to look like, what color is it going to be? It's going to be orange, I
Okay. So it's going to go from there up to there, right? I'll just keep it going. Like so. That line right there, everybody agree? Okay, that is what we call a secant line. A secant line is defined as a line that intersects a curve in two or more places. Okay, and so we don't care, maybe this function wraps around up here and intersects it again. We don't care. All we care about is that, locally speaking, it connects these 2 points on the curve. And so a slope of a secant line is what we define as an average rate of change. Okay, so there's a new, that adds to your evolving understanding of average rate of change. We're going to associate it always with the slope of a secant line. And so what would that be then? So the slope of a secant line is just going to be change in y over change in x, right? Well, what's the change in y here between these 2 points? Like if I were going to draw a slope triangle, how much am I rising? Okay, good. So this y value, f of x plus delta x, minus this y value, f of x, right? So change in the function, or change in y, and how much are we running? Delta x, yeah. Okay, good. All right, so then that's easy, right? But where differential calculus really came from was the quest to answer the question, all right, but I want to know an instantaneous rate of change. I want to know the rate of change at a point, not between 2 points. So that looks like, for example, if I want to go down here to this point at x f of x, if I want to know what the slope of the curve is at that point, that's something that before calculus we had no ability to do. That's what calculus gave us the tools to do that. What kind of a line would that be? What do we call a line that intersects a function at only one place locally and has the quote-unquote slope of the curve? Remember? Goes back to probably geometry. This would have talked about this.
Tangent.
What's that?
Tangent.
Tangent line. Yeah, tangent line. So let's draw the tangent line in here. So tangent line is going to look something like maybe, something like that. That's not too bad. To say so myself. There we go. So there's our tangent line, right? Okay, but how are we going to calculate that? Before I ask you that question, do you understand that it's a weird concept, but do you get that that really is the slope of the curve?
No.
Okay, that's a little mysterious, isn't it? Let's explore that graphically. Okay, so what if we go, all right, let's see, I'm going to go to I must be hungry, it's Quiznos. No, I'm talking Desmos here. So let's do, I want to do, how about if I just do x squared? Okay, and then I want the line, I got to think for a second here, so I want the line. Okay. Okay, so I want the line. Okay, so how about this? We go line. Okay. Yeah, that's good. Okay, so we're saying that, thank you. Oh, all kinds of good stuff here. Holy smokes. Lots of good stuff. Does someone want to pass these out while I get this thing set up? A little help, Ralph. Thank you, Miranda. Thank you, thank you. There you go. Okay, so this concept of a line having the slope of a curve. I'm claiming here that the blue line and the burnt umber is what I'm calling that color. The burnt umber curve, by that, have the same slope at the point of tangency, at the point where they intersect. Okay. It doesn't really look like that now, does it? If I go over here and find the point of tangency, it's at 2, 4. Okay? So let's hold that thought, and I'm just going to zoom in. I want you to witness the magic as the line becomes the curve. Do you even see? Oh, there's a little bit of burnt umber down there. But I gotta find it. See, there's the point of tangency is right there, right? Yeah. So let's get that in the middle. Okay, now you can't see any, right? I didn't have to zoom in that far. But you see my point. If we zoom in sufficiently far, if the line has the slope of the curve, then they become indistinguishable, right? Just like if aliens were to beam down to Earth out in a wheat field outside of Pendleton, you know, they would think that, boy, this planet is pretty flat, right? I don't see any evidence that this is a spherical planet. It looks pretty darn flat. In order to see that it's pretty flat, all they would have to do, and maybe some people are still convinced that the Earth is flat. Well, we'll have to send you up in a satellite to prove otherwise, or at least a plane that goes really high. If you zoom out, though, how do you zoom out? Well, if you were to get in a spaceship and zoom out, you'd start to see that, okay, this is what happens. Yeah, it looks pretty flat at this point, but as I zoom out, I can start to see that the curve does appear, and it deviates from the line, right? Astronauts standing on the moon could block the Earth out with their thumb, right? So it was pretty obviously spherical, right? Or at least it was round. Maybe it was flat and round. They couldn't prove otherwise, but I'm pretty sure it's spherical. So anyway, so we want to be able to find in calculus, our goal is, we want to be able to find how do we come up with that slope, right? If we go back to this graph, I can ask, oh gosh, what do I do? I never know. I never know what I'm doing. So if I go to this line right here, I can ask, well, we know what the line is. What's the slope of the line? 4. Yeah, so that is definitely the slope of the curve, f of x equals x squared. At the point 2, 4, the function has a slope of 4. That's weird, right? Slopes, we're not used to saying that something that's not a line has a slope, but now in calculus we do. If we focus in far enough, zoom in, it does look like a line, and it does have a slope. So how do we come up with that? How do we come up with the slope of that green line? It's the slope of a tangent line. And that's the question we want to ask today, we want to answer today. Any ideas? What can we do? I could I approximate it? Could I maybe just at least get a good estimation of what the slope of the green line is? Using the concept I already know pretty well, that's the slope of the secant line. What do you think? Josh, you got an idea? Well, you're shaking your head, maybe you don't. Do you have an idea?
Not you.
Okay, all right. Anybody have an idea how we maybe could do this, using a secant line? Oh, well, okay, so, yeah, don't confuse, now, when we say, yeah, I should distinguish. Secant line here has nothing to do with the secant function in trig. Yeah, they're completely, I don't know, we do that a lot in math, we recycle things. I guess we're environmentally conscientious. So, any ideas, though? I mean, right now, the orange line looks really different from the green line. How come?
Because it's like 2 points.
Okay, so, yeah, well, the secant line, the 2 points are pretty far apart, right? The curve changes pretty dramatically from here to there. Say it again. I mean, there's nothing set in stone about what delta x is. I just picked it randomly. Could I do something to delta x that maybe would make that orange line look more like the green line?
Make delta x smaller.
I'll make it smaller. Yeah, what if I migrated this point along the curve closer to x, f of x, right? So for example, what if I let delta x be a lot smaller? What if I put the point right here, for example, right? Now if I drew that secant line in, see if I can change this thing, what I can do. Oh, I can't do that. All right. There we go. Oh, that's fun. I love playing with my toys. So I'm just going to bend this thing down so it looks kind of like that, right? That's better. Agreed? And I could go further with it, right? I could make delta x, if this is the point that I'm using right here, and this is what I'm now defining as my new delta x, I could even make it better if I went closer, though, right? But if I want to have a perfect, I mean, really, these are just approximations. If I want to have the exact slope of the tangent line, though, what could I do with that process? I could take a limit, right? I could take the limit as delta x approaches, well, as delta x, as the point approaches this point, but that means delta x is approaching what? There's my delta x for the blue point. There it is for the purple point. As it approaches 0, right? See what I'm saying? And then that would be, the answer to that limit would be the slope of the tangent line, wouldn't it? Everybody agree? You get the idea? Now, remember that when we're talking about a limit, we can never get there, right? The limit never gets there, but the value of the limit is, as long as there's not a hole in the function or something, the value of the limit ends up being what the function actually would be if I could get there. You get the idea? So even though we can't divide by 0, we can't let delta x go to 0, we could take a limit as x approaches 0 and see what the behavior is, right? Because that's really, I mean, we're trying to get those lines to overlap so well that it becomes essentially a perfect overlap, right? So we'll just take a limit of the slope of the secant line as delta x approaches 0, which we'd write as the limit of f of x plus delta x minus f of x over delta x as delta x approaches 0. Okay? Well, let's go back to the problem, and this is, by the way, this is what we're going to end up calling a derivative, because that's what a derivative seeks to do, is find the slope of a curve at a point. Okay? It's an instantaneous rate of change. It's the slope of a tangent line. So So we're gonna call this, I'll publish these notes. You guys can access these on Moodle. So if this is what we're defining then as a derivative, and the notation we use, thank you. Oh, Tyler just left. I gotta get this real quick. Tyler, here, you got a note. Fire note before you go. No, thanks. Okay, so the notation we use for a derivative is we call it f prime, right? And that's equal to the limit of f of x plus delta x minus f of x over delta x as delta x approaches 0. Okay, we use the prime notation. That's one way to do it. It's a really good way to do it because prime means change. Think back to like geometry. If you put a prime, when you do a transformation, if you start with a point that has coordinates x, y, and then you reflect it or rotate it or translate it, you call the new coordinates x prime, y prime, right? Because they changed. Well, same kind of thing here. We took our original function and we changed it to get this new function that's called a derivative that's going to give us the slope of the secant line. Okay, now this is so cool. You guys are going to love this. So let's go to the example we looked at on Desmos. Remember, we took the function f of x equals x squared, right? And we wanted to know what the slope of the secant line is at x equals 2, right? Or the slope of the tangent line at x equals 2. Okay. How do you think we're going to do that? What do you think? Okay, well, what's our function in this case? X squared. Okay. So then if I want to find our derivative, how's that going to be defined then? It's going to be, this is always going to be our limit definition of a derivative. This is the fundamental definition of a derivative. So what's that going to look like for our defined function? Okay, so the limit of what's f of x plus delta x, if f of x is x squared. And what's that going to be? So if f of x is x squared, what's f of 4? 16. How'd you get that? 4 squared, right? What's f of a? A squared. What's f of hand? Okay, good. So what's f of x plus delta x? X plus delta x quantity squared, right? Okay, so we get the limit of x plus delta x squared minus f of x. That's x squared, right? And I think, Lily, you were telling me what this whole thing was when you expanded it out, weren't you? I was thinking maybe you were. Okay. Well, that looks pretty familiar, doesn't it? If I try to evaluate that directly, what do I get? So yeah, that'd become on the top, that term would go away. I'd get x squared minus x squared.
0 over 0.
0 over 0, more work, right? So what's the more work look like here? What do you think I'm going to do? Okay, I'm going to expand out the top, right? I'm going to have to just simplify this thing, right? And then eventually I'm going to have to be able to do some factoring and cancel, right? So I get the limit of, what is that expanded? Okay, plus, yeah, 2x delta x plus minus over delta x as delta x approaches 0. Okay, what can I do now? Okay, good. I can do some horizontal cancellation. Horizontal cancellation means cancels to 0, not to 1, right? So the x squareds go away. And now look what I'm left with if I do that. I'm left with just that stuff. What can I do now? Factor out of delta x. Good, because that's what I've got to cancel, isn't it? Right? So I get the limit of delta x times what on the top?
2x plus delta x.
Divided by delta x. Okay? As delta x approaches 0, I can vertically cancel the delta x's, so they cancel to 1. And now if I take my limit, right, well, let's write this down one more time. So I've got the limit of 2x plus delta x. As delta x goes to 0, that term goes away. So what do I get for my answer? 2x. Okay, that is incredibly powerful. Look what we just did. Did we come up with a specific answer? I mean, we did, kind of, but we're seeking to find what the slope of the tangent line is at x equals 2. Ah, yeah, okay, but look, our answer is general. I didn't have to pin myself down to x equals 2. I could have said x equals 1 billion, right? This function is going to calculate the slope of the tangent line at any value of x I choose. That's unbelievable, right? We just came up with a new function whose job is to find the slope of the original function by doing that process. Doesn't that just blow your mind? I mean, that's amazing what we just did. We took some idea of this random general picture, right? And we said in general, if I want to find the slope of the tangent line at this point, well, we're just going to bring this right-hand point so close to the left-hand point that the two points that define a secant line effectively become a single point that defines a tangent line. Totally generally, we didn't say anything about any specific function, right? We just looked at this and said that's the process we would have to follow mathematically to come up with the slope of a tangent line. Take the limit of that as delta x goes to 0, right? Pretty straightforward, not a big deal. So we defined this process then that we call the derivative, and we're just going to do that. We're just going to take the limit as delta x goes to 0 for those 2 points that we drew on a random picture. Now we can apply that to a specific function, and look what we got back. We got back a derivative function. We found out that f prime of x equals 2x. So f prime of 2 is 4. That's huge. So we know that the slope of the tangent line at x equals 2 is 4, right? So finding, there's our answer. What if we want to go a step further? Yes, ma'am?
I don't get how you plug it in.
Right,
How you take that,
right here.
how you take the derivative equation?
So how we take this and plug in this,
Yeah.
fx squared. Okay, so then what we're just always going to say is we're going to start with general and we're going to work to specific, right? So this is totally general. First step is going to be, well, what's our function? What's the rule? Right? The rule means kind of the equation, right? So our function rule is f of x equals x squared, right? So then our rule is whatever we're inputting into the function is just going to get squared, right? So let me color code this thing. So this thing becomes that, right? And this thing becomes that. Get the idea? Okay? And then now we just do our calculus, right? Now we just take the limit, or really it's pre-calculus now. The calculus part, if you want to call it calculus, is just that relationship. Once we apply that to our specific problem, this really becomes just a bunch of algebra, the kind of algebra we've been practicing. We might call it pre-calculus stuff, right, analysis stuff. It's a calculus class, but we haven't really learned the calculus tricks yet. There's going to be a trick that'll make this whole process shorter. But you get the idea? And then so once we're to here, this is a problem I probably did give you guys this problem when you were wrestling with taking limits, right? When you were doing limits, more work type limits, where you had to resolve the indeterminacy. Without knowing it, I was sneakily kind of giving you some problems that now are going to be a piece of cake, right? So let's do one more of those. Oh, let's finish this though. So we know the slope of the tangent line is 4. What if I want to know the equation of the tangent line? What are the ingredients for the equation of a line?
Slope and
The slope in a point, and we could turn the point into a y-intercept if we want to. We just need a slope and a point, don't we? Well, we've got a slope, right? This is m. What's the point? If this is my function and I want to find the tangent line at x equals 2, Richard, how could I find a point? The x value is 2. How would I calculate the y value of the point of tangency? Yeah, square it. Yeah, I just evaluate my function at 2, don't I? Right? Okay, so we could say there's my slope. My point is going to be at x equals 2, y equals f of 2, which is 4, right? And so there's the point of tangency, right? Because that's the point where the tangent line is going to hit the function. So we've got the point of tangency. We know that the slope is just the derivative evaluated at x equals 2. So now we've got a point, we've got a slope. It's easy, right? Now we just do, how did that get changed? It's really bugging. Well, deal with it later. So now the slope of the line is just going to be, we want to put it in y equals mx plus b form. So this is just algebra 1, right? We're going to plug in 4 for m. So we get y equals 4x plus b. We'll use the coordinates of this point, that solution, to solve for b, right? I can plug 2 in for x and 4 in for y. And I get 4 equals 4 times 2 plus b, so what's b? And so we end up now with the line y equals 4x minus 4, right? And let's go back to our picture. It's not coincidental that that's exactly what I graphed, right? Make sense? Okay. So try one of these on your own. I want you to find, how about, okay, try this one. Try find the equation of the tangent line for that curve at x equals 3. take a couple minutes and just try to at least get things set up, and then how about if we finish it together?